Okay, so welcome. Today I want to talk to you about systems and a little bit more terminology just to start in about what does all the lingo mean when we talk about systems and properties and states and stuff like that. So this is the very foundational elements of what we're going to be doing on an everyday basis when we deal with thermodynamics. One of the most basic quantities that we can talk about, or kind of ideas that we can talk about, is the idea of a system. So what is a system? Well, I'm going to define it down here. A system is a quantity or a region chosen for study. So what do I mean by this? If you had a specific, let's start with quantity, if you had a specific amount of matter, amount of mass that you wanted to study, and only that, you don't want to study anything else in the universe, that's your system. It doesn't always have to be an amount of mass. That's why we have the word region. It can be a volume in space, an area in space. So I could say my system I want to study right now is this area of the chalkboard, all right? So that would be an example of studying a region. And maybe, depending on what type of system, the mass in this region is changing, all right? So it's either a quantity or a region. And we can choose this. That's an interesting point about a system. They're chosen arbitrarily. So, for instance, somebody might choose their system to look like this, and then I may come along and I may say, well, that's interesting, but I want to study this as my system. And see how I've included here part of something different than they've included in their system. Now, at different times, there's different ways of choosing systems that are easier or more convenient or more suitable for solving problems. And so sometimes you might hear me talk about, okay, well, this is obviously how we want to choose our system. All right, and that's all well and good, but I just want you to understand that I'm still imposing that on the system. And in principle, it can be chosen to be whatever we want it to be. All right, so we've defined a system. The next logical thing to define are the surroundings of that system. Surroundings. So, the surroundings of a system include the mass and the region not in the system. Okay? This is the entire rest of the universe. In my example where I chose a system, by definition, when I choose that to be my system, everything else in the whole universe is outside of my system. It's part of the surroundings. And the surroundings do enter in, because sometimes we need to look and see what types of things are coming in from the surroundings. Is there mass coming in? Is there energy coming in? How are the surroundings of a system affecting the system? Okay, the third concept is that of the boundary. So if I have my system, and what I actually drew was the boundary, I'm going to make this a little more concrete this time. I'll draw something like a piston, all right? So here's a piston, and it moves, let's say, down this way, and in here we've got some gas or liquid or something. So here, there's a well-defined boundary to the system, and I'll do it in a different color. If I choose my system to be this fluid that's inside of here, the boundary is what I've marked out in red. Now, on a theoretical basis, the boundary is actually a mathematical concept. It's infinitely thin. Our book talks about that, how there's actually no real world makeup to what we can call the boundary of a system, but it's a very, very useful concept, because as we're just arbitrarily choosing systems to be whatever we want, what we're doing when we choose systems is setting boundaries. So in our minds, we're going, here's where I'd like to put this imaginary hypothetical boundary. Now, boundaries themselves, they can be fixed or they can be movable. Okay? And you you guys are probably pretty comfortable with this already, but since our book takes time to talk about it, I want to talk about it real quick. I'll give you an example of each. Let's say that you had a piston that was moving up and down. Shouldn't have raised my piston, but I'll just say the side and bottom walls of that container I drew, those are fixed, they're not moving. And the top boundary where the fluid meets the piston, that's a fluid boundary, but it's movable in the sense that over the course of the study of our system, that boundary is going to change in its position. All right. The other thing that our book talks about a little bit is that the fact that a boundary itself can be actually physically defined in the real world, or it can be imaginary. So if I have this, which is a nozzle, and let's say fluid's coming in, and maybe this nozzle widens out the fluid, so the opening is larger than the input. Okay, right here, I may just want to study the system of the fluid within the nozzle. So obviously, I might put a boundary here along this real wall. There's some metal here or something. But then I may say, well, those are my side boundaries, because I don't care about what's happening way down here, down the pipe, or the turbine, or whatever's after this nozzle. All I care about right now is studying what is happening within this region of space. And so I can put an imaginary boundary there, okay? Again, this all goes along with the fact that I have the freedom to choose where this boundary goes. Okay, so that's what a system is. There are, for the purposes of what we're going to do in this class, 3 types of systems. And so I'm going to draw 3 systems here and show you the difference. The first system is called an open system. And what that means, what we mean when we say open, is that we can exchange mass with the surroundings, and we can exchange energy with the surroundings. So across the boundary of the system, there can be a change in mass or energy, all right? Open systems are also sometimes called control volumes. Okay, and if you have trouble remembering that, one way to think of it is look at the definition of system. It's either a quantity of mass or a region. Well, if the mass here in our system is changing, then we must have picked this system to be a region of study. And that's why they use this term, because the volume, the region, is controlled. All right, that's an easy way to remember it. The next type of system is called a closed system. And in a closed system, energy can still go across the boundary between the surroundings and the system, but no mass, okay? X to indicate that mass can't enter or exit the system. And so we have a fixed amount of mass in our system. For that reason, this is sometimes called a control mass, all right? Now the third type of system is isolated. And you can probably already guess what that is. Just a big X for mass and energy. All right? Neither mass or energy can permeate that boundary. So it can't cross from the surroundings into the system or vice versa out of the system. All right? So these are the 3 categorizations of system. Next thing I want to talk about are what our book calls system properties. All right? So I'm going to define system property. And this is anything about a system that we want to study. All right? Really, the only distinction here, the only note to make, is that there are things about systems that we sometimes don't want to study. All right? So if I'm studying the density of a liquid, it may not matter to me what color that liquid is. So in that case, the color of it is not even going to be included as a system property. All right? It's sure something about the system, but it's not something that I care to study. So anything at all, and these can get pretty abstract. We're going to go through some examples of them in a minute. But anything at all about a system that I care to study, that's what a system property is. Now, properties of a system are broken down into two main categories. There's intensive properties, and there's extensive properties. And I'm going to define both of these. So extensive, one of the ways to remember this, is that if a property is extensive, it cares about the extent or the size of the system. So extensive properties, here's the definition now, they depend on the size of a system. All right, so what are some examples of things like this that depend on the size of a system? One example is mass, another one is volume. And for volume, I'm going to write my V like this with a little hook on it. The reason for writing it like that is that we may get into dealing with velocities later in the class, and I don't want to use up my normal letter V that I use for velocity. Okay, so I'm going to try to remember to write my volume with that little hook on it. All right. So mass, volume, and then another thing, maybe energy. It's the energy of a system. Extensive things. These things depend on the size. If we changed the size of the system we were talking about, then these things would also change with it. All right. Intensive then is the opposite. So they don't, and then what I wrote down there, they don't depend on the size of the system. So what things don't depend on the size of the system? Well, some examples are the temperature. I mean, think about temperature of a room, right? If you had a large room or a small room, and you say you took a room and you changed the size of it, the temperature is a property about that room, right? It's a system property, but it's not going to change when I change the size of that, all right? Pressure is another one, and rho for density, okay? So I'm going to draw this letter really big because we're seeing this early on, which I think is good. And I want to make a note of how we write this. This is the Greek letter rho. Okay, spelled R-H-O. And this is not a P. The biggest problem that I see with notation in this course is people making rhos into P's. We have to reserve the letter P specifically right now for pressure. Okay, so this is the difference. This is how I draw a P. This is how I draw a rho. So I just want to get really early on that confusion out of the way, all right? So this is the Greek letter rho, and it's used for density. So that's what I wrote here. Density is an intensive property. It doesn't depend on the size of the system. So there's a cheater way that we can think about determining whether a property is intensive and extensive. And I like this method a lot. Think of a system, all right? I'm going to draw this box being our system. And this system has tons of properties. It's got all the ones we listed plus more. There's temperature, pressure, density, mass, volume, energy, lots more properties. If I were to take an imaginary partition and divide this system in two equal halves, let's say, just for the sake of simplicity, would the property that the system had change? All right? If it would change, then it's extensive because it's depending on the size of our system. So volume, for example, obviously, if I take a system and I cut it in half, I'm halving the volume. That extensive property of volume is changing. But if a property wouldn't change when I halve the system, that's intensive. So this is a really easy way, if you're ever getting confused, to distinguish between these two, is just play that little mental experiment of taking your system and cutting it in half, dividing it in half with an imaginary boundary, all right? Okay, So, there's something called a specific extensive property. So I'm going to define this. And specific, I'm not using colloquial language. I'm going to put it in quotes because specific is actually the scientific term here that we're learning. So specific extensive system. All right, so we're only talking about the properties that depend on the size of a system. And what a specific extensive system is any property, all right, divided by the system's mass. So I'm going to take some extensive property, specific extensive property. I'm going to take some property and I'm just going to divide by the mass, and then I get the specific version of whatever that property was, right? So, for example, I could take the volume. So my property is going to be the volume. If I divide that by the mass, I get what's called the specific volume. And the rule for this is that whatever the letter was representing the property, for the new symbol, we're just going to use the lowercase version of that letter. So this is a lowercase b. I'll write that for you. So we're going to lowercase the letter because we divided by the mass, and we're now going to call it, we're going to put the word specific in front of whatever we were calling it. So we took the volume, and now we have the specific volume. Okay? And I'm just defining this for now, but this is something that we get into a lot more later. And this is something that we do with extensive properties, is every extensive property then has a specific version associated with it. Okay? So, the other thing I wanted to mention about system properties is that there's a lot more examples. So let's look at these examples that I wrote right here. There are a lot more examples of properties than just these, and they can get pretty abstract in their definitions. Some of them we're going to talk about in this class, and some of them we're not. So I'm just going to give you a few examples. That's not me promising that we're going to study them, but one is the enthalpy. If you ever heard that term, we use H for it. There's something called entropy, which we're going to briefly touch on, and we use S for it. There's something called Gibbs free energy, which we use G for. And there are many, many more. So I'm going to do a giant ellipsis. I just want to emphasize that as we talk about properties, don't get too comfortable thinking that you can have a complete list. Oh, these are all the properties. No, there could be lots of properties, and we could really introduce properties at any time throughout the course, all right? Okay. So the next thing that I want to define is what we call a state. Okay. If I were you, I'd just write down a lot of these definitions as we're going through, because a lot of this is definitional, but it's really important because I'm going to start using this language and I'm not going to go back and explain it every time. Okay, so I'm going to write down the definition of a state. It's a collection of all properties we are studying. So, the definition of a state depends on the definition of a property. We have to have already defined a property, because a state is now a collection of them. So let me just write down a state. And this is just my notation. I'm just going to write it as a collection, and we might care about the mass, the volume, the temperature, and the pressure. All right? That's my collection. Mass, volume, temperature, and pressure of a system. All right? And so this would define then what our state is. Let's say, for my example of this state that I've defined, let's say that I change its position. All right, so here's a bottle of hand sanitizer. I can ask about what the mass, the volume, the temperature, and the pressure are inside this bottle. If I then take it and move it to somewhere else, I've changed the position, so let me write what I've done. All right, change the position of that. But have I changed the state? Okay. Not in this example. The reason I haven't changed the state is because it's not in the collection of properties that I'm caring to study right now. All right. These are the properties I care about. Now, if I were to widen my definition of what the state is, and I were to include in this collection the position, which we will, then changing the position would change the state. Okay? So another example of a state, let's say, and this is just an abstract example to prove the point, all right? I'm not saying there's anything like this in real life. But let's say that our state is just the temperature and the pressure. Okay? That's all that's in our collection. Now, previously our state had the mass in it, but now it doesn't. So now I want to change the mass. Well, again, since now I've limited the amount of properties that I care about studying, and I've decided, you know what, I don't care about the mass. You can change it all day, and you're not going to be changing the state. All right? Whereas, like with position, if I include it and change the mass, now I've got a different state. I've changed the state. All right? So, the state is a collection of properties, but it's not necessarily just any willy-nilly property you can think of. It is specifically the properties that we care to study. All right? So, another definition for you. And this one's closely related to talking about the properties. Equilibrium. Now for right now I'm defining this, okay? I'm going to talk a lot more about this when we get to concrete examples of specific properties. But equilibrium, definitionally, means that the property, whatever property, so I should say equilibrium of a property, the property is not undergoing changes, okay? And again, there's all sorts of asterisks and caveats that go with this, but this is the basic definition. We kind of use this in everyday colloquial language too, when we say something's in equilibrium. What we're saying is that that property, whatever property we're studying, happens to be in equilibrium. So, is it possible that one of the properties in my state might be changing, but another property might be in equilibrium? Well, yes. Because the equilibrium has to do with the specific property that we're talking about. So we're not saying that for one property to be in equilibrium, the entire state is in equilibrium. Everything is in equilibrium. That's not what we're saying. We're just saying that whatever property we're talking about, that can be in equilibrium. So there are different types of equilibrium that our book defines, so I want to go through them real quick. If the temperature is what's in equilibrium, it's called thermal equilibrium. Okay, and we saw this in the lecture for Wednesday too, where the word thermal comes from. If the pressure is what's in equilibrium, then it's called mechanical equilibrium. Okay, and another abstract example, our book talks about chemical equilibrium. That's when the Gibbs free energy is in equilibrium. And I don't think we'll deal too much with chemical equilibrium, but since the term is in there, okay? And so there can be other types of equilibriums too. Any property that we have can have associated with it an equilibrium, okay? All right. The last thing I want to do is look at something called the state postulate. State postulate. Now, first I'm going to write down what the state postulate is. It's kind of a long definition, and then we're going to go into talking about kind of what some of these definitions are. All right? So this is how our book defines the state postulate. For a simple, compressible system, we need only two independent variables to fully determine every other property. So remember the definition of property. It's something in the system that we've chosen to study, all right? It's part of our state. That's why state, so it's called the state postulate, all right? So it's not just any property, but properties that are in our state that we've chosen to study. So what do some of these terms mean? Well, simple compressible. This, all right, simple compressible. Basically, what a simple compressible system is a system that is not affected, or we're not taking into account effects by certain things. So one would be electrical effects, magnetic effects, motional effects. So the example that I gave you of the beginning of moving the position of the sanitizer bottle, okay? That motion of me moving it back and forth, that's not taken into effect. And what else? Oh, surface tension. Surface tension effects aren't affecting the system, and then gravitational. Okay? And this is in the textbook. If you want to read them, there's a write-up talking about this. So this list is what isn't affected in a simple compressible system. All right? And I know that's kind of a roundabout way of defining it, but you could also think of me defining it as saying, okay, a simple compressible system is a system that's affected by any other thing besides this list. All right? So any other effect, we can deal with it, but we're not going to deal with the stuff on this list. That means we're good to go. State postulate applies. All right? So, simple compressible system, we need only two independent variables to fully determine every other property. So if you remember on Wednesday for the lecture, we talked about how we had the base SI units. And I emphasized that word base as meaning that you couldn't write one of the units on that list in terms of a whole permutation of other units on that list. They're somehow fundamental. They are basic. That's what the word base meant there. This is the same idea, that we only need two independent variables, that every other state property or variable can be written as some combination in terms of two basic ones. So we just pick two, and then we can define the whole system. Every other property in the system can be written in terms of those two. Okay? That's what the state postulate is saying. Now, one important caveat before I let you go on the state postulate is that those two base properties that we choose, they can be different. So I might say, I have my whole system, I've got this whole list of properties, and I want to use these two to define all the rest. But somebody else, my buddy, might say, well, I also want to do the same thing. I want to describe all the rest in terms of two, but I want to use these two, and that's all right. He can choose a different two properties than me. The state postulate doesn't talk about which properties we have to choose. The state postulate just says that in these simple compressible systems, you only need 2, all right? So it's just a guarantee of a minimum. You have to have at least 2, all right? The last thing, okay, yeah, I forgot I wanted to talk about process. All right, so let's talk about processes real quick. I'll erase this half of the board. So a process, we almost hit it earlier when we were talking about equilibrium. A process is simply changing the equilibrium of a system. So let me write that down if you're taking notes. I'll write down the definition. Oops. Process. Okay. Process is a change. Now I could write a change in some, at least one, several of the state properties of the system, but we have a word for that. We just call it state. Remember how we define a state? It was just the collection of properties we care about. So I can simply write a change in state. That's what a process is. Okay? Now, the way we talk about processes is we can actually graph them. And we're going to be doing some of this semester. So I'm going to give you an example, but first let me do it in the abstract. Write out my XY coordinates. And on the x-axis, I'm just going to label this property A, right? Some property that we're talking about. And I'm doing it like this because this explains the diagram that's in our textbook, where they just have it labeled property A. And then up here on the y-axis, I've got property B. So all they're saying is essentially what I just said about the state postulate. They're saying that we're just going to take 2 of them. We don't care which 2, this is going to be general. Some 2 properties about the state that are different. And now, because we've created an XY coordinate system, we can plot a point corresponding to our system. So what would that look like? All right. So I would take my system and I would measure property A. Let's say property A was temperature. All right. I would say, what is the temperature of the system? Then I would do the same thing for property B. Take my system and I'd measure property B. And then, once I have those 2 measurements, I would plot them as a coordinate. And the coordinates as a point, the coordinates of this point would be how much of property A and how much of property B does my system have. So I'm plotting the system as a point in a coordinate space. And I know it's pretty abstract, but I'm just going to label this point as state 1. Okay? And then I could have another system or another state if I change these properties, and I could plot it as a different point. So up here I would say state 2. And I do the same exact process to come up with where this point goes. But in this case, you can see that we've risen in both property B and in property A. And so from when I measured this state to when I measured, this is state 2, to when I measured state 2, whatever property A was has increased, and whatever property B was has increased. And one more term here, if I draw the path between the 2, this is called the process path. Okay, so some process changed state 1 to state 2. So that's the abstract. I promised you that I'd give you an actual real-life example of this. Let's say that this is pressure and this is volume. So property B is the pressure, property A is the volume. That means that all I do is I get my measuring stick, or maybe I read the label on something and I say, okay, what's the volume of it? And then I have a value along the volume axis, and then I say, what's the pressure of it? And I have a value along the pressure axis. I can then plot it. And if it changes, I can plot it again. And if it changes, I can plot it again. I can keep putting points corresponding to my new measurements. And all of these changes, no matter what it does, it can change between these 3. Maybe there's one up here, it goes up here. Any change, these are the process paths. Okay? That's where I want to stop for today. A lot of terminology, a lot of definitions. but now you guys kind of know what we're talking about when we throw around these terms like state and system and properties. And this idea of plotting points to correspond to the state, or showing you the state of a system, this is going to turn out to be really fundamental. All right, so we're going to talk more about this when we actually meet on Monday. So I'll see you then. Thank you guys.